TLS-1.3 provides a secure channel between two communicating peers, but some encrypted traffic has a longer shelf life than the cryptography protecting it today. An attacker may record traffic now and store it, hoping that a future quantum computer will be able to break the algorithms used during the original handshake. Post-quantum hybrid key exchange addresses this risk by strengthening the key agreement part of TLS-1.3. Welcome everyone to the Inside Java Newscast, where we cover recent developments in the OpenJDK community. I'm Ana Maria Mihalchano, Java developer advocate at Oracle, and today we're going to look at how hybrid key exchange algorithms for TLS-1.3 can enhance the secure network communication of your Java applications. Ready? Then let's dive right in. Quantum computing poses a future threat to widely deployed public key cryptographic schemes based on RSA and elliptic curve Diffie-Hellman. Even though large-scale quantum computers capable of breaking these schemes do not yet exist, the migration is already urgent because of the harvest now, decrypt later threat. An attacker can harvest encrypted traffic today, store it, and attempt to decrypt it later once sufficiently powerful quantum computers become available. To help protect TLS against this risk, the Internet Engineering Task Force TLS Working Group has developed a framework for hybrid key exchange in TLS-1.3. A hybrid key exchange combines a traditional algorithm with a quantum-resistant algorithm. The resulting session remains secure as long as at least one of those two algorithms remains unbroken. The Java platform has already been preparing for this transition, as Java 21 introduced the Key Encapsulation Mechanism API through JEF 452, and Java 24 added support for ML-KEM through JEF 496. The next step is bringing these post-quantum building blocks into the TLS implementation. So, in JDK 27, the TLS-1.3 implementation is enhanced with hybrid key exchange schemes that combine ML-KEM with traditional ephemeral elliptic curve Diffie-Hellman. These three new hybrid TLS-1.3 schemes are proposed in JEF 527. The first is X25519 ML-KEM 768 that combines the traditional X25519 elliptic curve Diffie-Hellman exchange with the post-quantum ML-KEM 768 algorithm. The second is SECP256R1 with ML-KEM 768. And the third one is SECP384R1 with ML-KEM 1024. In TLS terminology, these key exchange schemes are called name groups. The JDK will add these names to the Java Security Standard Algorithm Name Specification using the names defined by YANA. During a TLS handshake, the client sends a list of supported key exchange schemes in a preferred order. With this enhancement, the JDK's TLS-1.3 implementation places X25519 ML-KEM 768 at the front of the default list, making it the preferred option when both the client and the server support it. That means that many of the existing Java applications can benefit from the quantum-resistant TLS without code changes, as long as they use the standard JDK TLS stack and do not already override the configured named groups. X25519 ML-KEM 768 is the fastest of the new hybrid groups and is the one most TLS clients are enabling by default. The other two hybrid groups are available but not enabled by default. If you want explicit control over the name groups, you can configure those with jdk.tls.namegroups system property or programmatically using SSL parameters set namegroups method. For example, you can create an SSL socket from the default SSL context, then retrieve its parameters so you can customize the TLS handshake before connecting. Use set name groups to define the preferred TLS-1.3 key exchange groups, for example, putting hybrid post-quantum options such as SECP256R1 ML-KEM 768 and X25519 ML-KEM 768 first, followed by the traditional fallback groups like SECP256R1 and X25519. Since you got familiar with the theoretical concepts behind the post-quantum hybrid key exchange in TLS-1.3, let's see how that works in real life. The easiest way to demonstrate how post-quantum hybrid key exchange works in TLS-1.3 is via a familiar application like Spring Pet Clinic, powered by the early access builds of JDK 27. To run the application over HTTPS, enhance the existing configuration with an SSL bundle to consume key store certificates and private keys. Particularly for this demo, the application configuration defines that Pet Clinic should start on HTTPS port 8443, use the SSL bundle named Clinic, load the server certificate and private key from a key store, and require client certificates through mutual TLS. That covers the Spring Boot side of the setup, while the choice of TLS 1.3 key exchange groups is controlled by the JDK. When deploying the same Java application across environments, JDK Java Options is a convenient way to apply JVM options consistently without changing the application code or the startup command. Now, for this scenario, I will use it to enable TLS handshake debugging via the -d javax.net.debug option, which lets us observe how the TLS negotiation happens and which key exchange group is selected. As the application started, go to a browser window and access the application. Because the application enabled mutual TLS authentication, the server is asking the browser for a client certificate. Now, the browser is searching its certificate store for a matching client certificate, and if one exists, the browser may prompt the user to select it, then send the selection during the TLS handshake. Now, let's check what the debug logs have captured by looking first at the client hello, the hello message sent by the web browser to the server. This client hello content shows that it supports TLS 1.3 and TLS 1.2, along with its cipher suits, signature algorithms with certificate status options, and of course the server name. Now, the supported versions portion of the client hello advertises its name group preference lists with x25519 ML-KEM 768 first, meaning it prefers the post-quantum hybrid TLS 1.3 key exchanged, followed by the classical groups such as x25519 or SecP256R1, and of course the finite field Diffie-Hellman groups. The key share section, on the other hand, is confirming that the client is not only advertising those named groups, but also sending the actual key material for x25519 ML-KEM 768 and x25519, allowing a compatible server to choose the hybrid group or to fall back to the classical x25519 if the key exchange is not supported. Now, let's also inspect what the server has chosen by looking at its response through server hello. Now, the server hello is the server's response to the client's proposed TLS options, and it confirms that the connection will use TLS 1.3 and selects a cipher suit for protecting the session. It also selects x25519 ML-KEM 768 as the key exchange group and sends its matching key share, meaning the server accepted the client's preferred hybrid post-quantum TLS 1.3 key exchange instead of falling back to the classical x25519. The long key exchange byte block is the server's key share material for the selected hybrid group, while the TLS-AS128 GCM SHA-256 is the symmetric cipher suit that will protect the application after the handshake and derives the shared session keys. Now, after the handshake is completing, the application traffic is being protected with symmetric encryption and, of course, using the negotiated cipher suit. Post-quantum hybrid key exchange in TLS 1.3 is a step towards protecting today's applications traffic against tomorrow's quantum-capable attackers. With JDK 27 introducing hybrid key exchange schemes, Java applications can gain post-quantum protection at the TLS layer without rewriting business logic. I hope this encourages you to start exploring post-quantum hybrid key exchange in your own application by trying the JDK 27 early access builds. And if you enjoyed this episode, give it a like, share it with your friends or colleagues, and subscribe to this channel for more Java content.